So section 6.4 is about logarithms. Now let me think back to a problem that we had in the last example. We had to solve equations in which both sides were recognizable after a little work as powers of 5 or powers of 3, and we figured out that the exponents have to be the same if the bases are the same. That's kind of how the trick worked. But if somebody gave me this problem, 10 to the x equals 7, you might be kind of stumped because they're not obviously powers of the same number. I don't see that this is 2 to the something or 3 to the something on both sides. But there has to be a solution, right? Because think of what 10 to the x looks like. At 0, 10 to the x, here's y equals 10 to the x. At 0, 10 to the x is 1. At 1, 10 to the x is 10. There must be some number where 10 to the x equals 7. Some number between 0 and 1 would cause 10 to the x to be 7. Well, it turns out the answer is something called log of 7. And I used my calculator to tell me it's roughly 0.8451. And sure, it's a number between 0 and 1. That log, by the way, is also known as, it's sometimes written as log base 10. So log 7 is a number, it's the number you raise 10 to in order to get 7. So 10 to the log 7 is 7. What's 10 to the log 3? Well, log 3 must be the number that you raise 10 to in order to get 3. So 10 to this number is 3. All right, 10 to the log 100 must be 100. Hey, I know what that is because this is, I already know 100 is a power of 10. Log 100 must equal 2. All right. What's the log of 1,000? Well, that's like asking, what number do you raise 10 to in order to get 1,000? And the answer is 3. So this logarithm must be 3. In general, y equal log x means that x can be obtained by raising 10 to the y power. Like logarithm looks at numbers, even if they don't appear to be powers of 10 to us, logarithm recognizes them as powers of 10 and tells us, hey, this guy really is a power of 10. Here's the exponent you raise 10 to in order to get this guy. Generally, there are logs with bases other than 10. When we write y equals the log base a of x, we mean that x equals a to the y, that y is the exponent you raise a to in order to get x. Look at that equation. That looks familiar. We've almost graphed that before. I say almost because we've graphed y equals a to the x, not x equals a to the y. What's this curve got to do with that one? Well, all they did is interchange the x's and y's. Remember? When you interchange the x's and y's, that takes the point 1, 0 on this curve and says that the point, I beg your pardon, the point 0, 1 on that curve means that the point 1, 0 must be on this curve. And when you interchange the x's and y's on a curve, you reflect that curve across the 45-degree line y equals x. Something like that. So that's what x equals a to the y looks like. But see, that's just another way of saying y equals log base a of x. So this and this are two different equations for the same curve. That doesn't surprise me because this curve probably has lots and lots of different equations. But it has one equation where x is a function of y and another equation where y is a function of x. This guy must have two equations too. If y equals a to the x, then another equation for this curve must be x equals, let's take that equation and just interchange the x's and y's. X equals log base a of y must be another equation for this curve. You recognize the relationship between log a and a to the x? They're inverses of one another. Log base a of x is the inverse function of the function a to the x. So a to the x and log base a are inverses of one another. One thing I should point out is that you can't take log base a unless a is bigger than 0. You can't, that's because to build an exponential function, a has to be bigger than 0. Usually, in a logarithm, I mean all the ones I see in pre-calculus and calculus, a is bigger than 1, to be honest. You could take the log base 1/2, or log base 1/10 if you wanted, but in practice these are all the ones that we ever see. So the difference would be if the base were less than 1, then this exponential curve would be decreasing instead of increasing. And the logarithm would take a different shape too. But I tend to think of all logarithm curves with base bigger than 1, all kind of basically having that same shape, because all exponential curves with base bigger than 1 have that same shape roughly. What's its domain? Well, the domain of the logarithm, the inputs for the log, you can kind of see in this picture. The x's on this curve. The x's go from 0 to positive infinity, not including 0. That's the same thing as the outputs on this curve, because these two functions are inverses of one another. The domain of the log is the same as the range of a to the x, and that's 0 to infinity, all the positive numbers. They're either you either think of it as all the positive y's on this curve, or all the positive x's on that curve, but it's the same. And the range of log base a of x, that's the same thing as the domain of a to the x. What kind of numbers can you stick into a to the x? Well, you can stick in any positive number, or rather any number into a to the x. The output has to be positive, but the input can be anything. So that must be the same thing as the range. On this curve, the y's go from negative infinity to plus infinity. They're going down to negative infinity pretty rapidly as x gets close to 0. That's why this logarithm curve has a vertical asymptote at x equals 0. Log is kind of famous for growing very slowly. If you plotted it on a calculator or a computer, its graph would appear to be growing so slowly that you wouldn't think it's possibly going off to plus infinity, but in fact we know that it does. So, what's the log base 2 of 8? So sometimes I see these things, I get pretty good at seeing them after some practice, but if I don't see it, I'll just put a little x here and rewrite it from this logarithmic form into the exponential form. What this would mean is x has to be the exponent I raised 2 to in order to get 8. Now do you see it? Sure, 8 is 2 cubed, so x is 3. All right, this guy must equal 3. Let's try another one. How about the log base 9 of 3? Don't say 2 real fast. What you're noticing is that 3 squared is 9. This is asking, what's the number I raised 9 to in order to get 3? Well, you either write that as a power of 9, or that as a power of 3, and solve it like we did in the last section. I'll try to do this is probably what most people would do. 9 is 3 squared. And this is 3 to the 1. So this exponent, I'll write this as a power of 3. These exponents multiply. 2x must equal 1, because 3 to the 2x equals 3 to the 1. So sometimes finding logarithms can involve a little head scratching. Two more types of problems to show you in this section. So the first are some equations. So logarithms are useful for solving exponential equations when the bases aren't the same and can't be made the same. And it comes from this, the definition of log. Log base a of x equals y is another way of saying that x is equal to a to the y. There are lots of problems where it's handy to take an equation that looks like something like this and rewrite it in that form, or vice versa. So here's one of these problems where I've got an exponential equation and it pays off to write it in logarithmic form. So log is the exponent. X plus 5 must be the logarithm of somebody. But who's it the log of? Is it the log base 7 of 2 or the log base 2 of 7? The base there is the same as what I've been calling base here. Right? To say that x plus 5 is the exponent you raise 2 to get 7 means that x plus 5 is the log base 7 of 2. So now I can solve for x. I'll just add 5 to, or subtract 5 to both sides. It's negative 5 plus the log base 2 of 7. That's something we could calculate, but on a no calculator exam like ours, we're done. Let me try another. How about this equation? Log base 2 of 3x minus 1 is negative 1. Okay, the x is inside this logarithm. Though it's in this logarithmic form, let's think about what that says in terms of exponents. That says negative 1 is the exponent I raised 2 to in order to get 3x minus 1. So 3x minus 1 must be 2 to the negative 1. Now it's just a linear equation. I probably pays to rewrite 2 to the negative 1. That's 1 over 2. But let's solve for x. I'll add 1 to both sides. That's 3 halves. And divide both sides by 3. 3 halves divided by 3 is a half. And we're done. The other type of problem I need to show you in this section are domain problems. So, remember before when we did domain problems, I said the way you start off a domain problem is to say that all the denominators in your function must be non-zero, and everything underneath an even radical has to be bigger than or equal to 0. Now there's a new thing. See, the domain of the logarithm is 0 to infinity. So if the logarithm appears inside your function, the log of whatever that is requires that that thing inside the log, that entire expression, be bigger than 0. I'll show you what I mean. Suppose some problem says to find the domain of the log of this function. Rather, the domain of this function, the log of this polynomial. So that's inside the log. The real problem is to find where is this positive. So I do a sign chart. It's already nicely factored for me. I'll do a row for x minus 1 squared, and a row for x plus 3, and a row for their product. I'll just review what I've got here for you. X minus 1 is 0 at x equals 1, but because it's a square, it's positive everywhere else. So that top row is all pluses but a 0, except for a 0 at x equals 1. The middle row is 0 at x equals negative 3. When x is bigger than negative 3, I plugged in like a million. A million plus 3 is positive. Positive over here means everywhere there it's positive, not just at the point I sampled. And to the other side it's negative. When x is like, I don't know, negative 50, negative 50 plus 3 is negative. I pick really huge numbers, so I don't really even have to do the arithmetic. I mean, negative 50 plus 3 is a negative number. So negative out there means negative all along that interval. And now I just use the rules I know for, multiplying positive and negative numbers. Positive times negative is negative, positive, positive is positive, 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 positive. Where either one of these guys is 0, that polynomial is 0. So remember, this domain problem boils down to some inequality. And this guy is already factored. So the inequality is, where is this thing bigger than 0? That's all the pluses I see here. So I finish the domain problem by saying the domain is everywhere there's a plus. It's the interval from negative 3 to 1, union the interval 1 to infinity. So there's one thing I have to tell you, more notation. E is a number that's important in calculus, kind of like pi is important in trigonometry. It's roughly 2.7. E is a common base for exponential functions. It shows up in exponential and logarithm problems. More than that, you really don't need to know. We're not going to calculate anything with E. And unfortunately, there's a different notation for the logarithm when we're talking about base E. So when someone writes ln like that, that's short for the log base E. So for instance, just as 10 to the log base 5 is 5, well, e to the ln of 5 is 5. ln of 5 is the log base E of 5. It's the number you raise e to in order to get 5. Let's try one more domain problem if you want to see one more. If not, this is going to be the end of this section. You can skip the rest. But here's another domain problem for those who want to see it. Let's suppose the problem says, find the domain of the natural log of this, 2 minus 1 over x plus 3. Well, one thing I noticed is there's a fraction involved. So that fraction right there says that x plus 3 can't be 0. I need x to be different than negative 3. So I have to make sure I throw negative 3 out of this domain. But there's also a logarithm. The logarithm says the stuff inside here must be positive, or I can't take its logarithm. So to find the domain, I need to solve this inequality. So this becomes kind of a review problem from chapter 5, I guess. Remember how to do it? You get a 0 on one side, you factor the other. The last operation we've done is the subtraction, not a multiplication or division. So I'm going to subtract these fractions. I just need to rewrite this first one so that it has the same denominator as the second. So I'll write 2. I'll think of it as 2 over 1. And I'm going to multiply it top and bottom. I'm going to multiply on top and bottom by x plus 3, and those really didn't line up very well. But let's see. So the first fraction becomes x plus 3 times 2 over x plus 3, and then minus 1 over x plus 3. Now I can add these fractions. I just add the numerators. So that I'm going to distribute while I'm at it. That's 2x plus 6 minus 1, or 2x plus 5. So I need this guy to be bigger than 0. Now it's really simple. I mean, the numerator and denominator are pretty simple linear functions, and I'm just dividing them. So let's make a row for each of the factors I see in the numerator and denominator. 2x plus 5 and x plus 3. And then I'll have a row for their quotient. Let's see. This is 0 at negative 3. This one is 0 at negative 5 halves. That's negative 2.5. So negative 3 should appear to the left of negative 5 halves in my drawing. I plugged in some points here like at negative 1 trillion. Negative 1 trillion plus 5 is definitely negative. So this must be negative until I get to there. And over here, something to the right of that, how about x equals 0? 0 plus, when x is 0, that's 5. So this is positive over here. And similarly, I find this is negative and then positive there. So what about their quotient? Negative divided by negative is positive. Negative divided by positive is negative. Positive divided by positive is positive. Now careful. What about these zeros? That's a 0 of the numerator. 0 divided by something is fine, that's 0. But this is negative divided by 0, that's undefined. So, I'm supposed to be solving where this guy, I'm supposed to be finding where this guy is strictly bigger than 0. That's all the pluses. The domain is all the pluses. And look, it excludes negative 3 anyway. So the domain of this guy is going to be the interval to the left of negative 3. Heck, too many negatives. Negative infinity, negative 3. Union with the interval to the right of negative 5 halves. And we're done.